Okay, so this time we're now going to do one-way ANOVA. Last time we looked at how to represent categorical variables in R. This time we're going to show how we can compare the means and see if there's a difference. So if we go to our layout, so it should be similar to when we did the two-sample t-test. But what we're going to do is our observations, we're going to have k groups, and we could have different numbers within each group. We're going to set up in this framework. So this first row is all the observations from the first group. And you see the first number in the subscript tells us which group we're in, and the second tells us which individual in that group it is. What we're going to do, so the yij, so this is the observed random variable for the jth observation in the ith group is iid, normally disputed. They have different means and all have the same variance. And the interesting question we have is the population mean for each group the same? So this is a one-way ANOVA, and we're going to do this using a linear model. So how do we do this? Well, what we're going to do is we're going to set up that our model is going to be that remember, eta is the expected value of the ijth variable is going to be equal to mu I. We're going to set that up as an additive model where we say, well, actually, there's an overall mean plus each group gets an extra alpha I. So this is the overall mean, and this is the extra bit you get. And obviously, the extra bit might be negative, so you might be less than the overall mean for the group. Problem is, this model is not identifiable. We've over-parameterized it. If you tried to write out this design matrix, you would have dependent columns because the first one would all be ones, and then you'd have basically ones for each group, and they would add up to the overall. So what we need to do is we need to add a constraint, and the first constraint, and the one we saw that R does, is we're going to set alpha 1 equal to 0. That's going to be our reference case. Basically, the mu is going to be the mean for the first group, and everything is compared to that. So here's my design matrix. I write all the observations for the first group, then the second group, all in one big, huge column. And here's my design matrix. The first one is my intercept, the overall mean, which will work out to be the mean for the first group. And then the first group is zeros everywhere else. And then we use the standard representation we saw last time. And here is our coefficient vector, the overall mean, plus the extra bit for group 2, group 3, up to group k. So now we can actually rewrite that they're all the same is equivalent to say the last load of coefficients, alpha 2 to alpha k, are all equal to 0. And we saw that last time in the last chapter where we started looking at testing multiple hypotheses. In that case, we saw that we use ANOVA. So here's our between groups, our within groups, our total. So what is the between groups? It's saying let's look at the distance between the sample mean of each group and the overall mean. So this notation, to remind you, y hat dot dot. The dots tell you what I sum over. So the bar tells me it's a sample mean, so it's 1 over n, summation of the values. And the dot says I've summed over the first subscript, the I, and I summed over the second one. The same again over here, you can see that yi dot tells you again, the bar tells you it's a sample mean, and the dot says I've summed over the second subscript, which is the j. So this first line, we're looking at the sample mean for each group, the distance from that to the overall mean, we square it and add them all up. And it's a nice thing if you look here, this here, how many yi dots here are there? There's k of them, because there's k groups. The y dot dot, how many of them is there? There's one overall mean. And see the correspondence with the degrees of freedom. You've got here k minus 1, k minus 1. See if it follows here. How many yij's are there? Well, there's n. That's the total number of observations. Minus, so this is each observation minus here now is its group mean squared. So there's n here. How many here? Well, there's k of them because this I is the groups. There's k groups, n minus k. And the final one, this is the distance between every observation and the overall. There is n lots of points here. There's 1 point here, so it's n minus 1. Really nice. And if the null hypothesis is true, if I take this number and divide it by this number, and then this number and divide it by this number, I'd get 2 estimates of sigma squared. If the null hypothesis is not true, then the first one would get larger. So the idea is if the hypothesis is true, then when I do that calculation of this bit here and then this bit here, I should get roughly 1. In other words, I can do an F-test. This is the first group, the between group sum of squares. So this is the normalized between group. This is normalized within group. And if the null hypothesis is true, this should be approximately 1. How far away from 1 can we test it? Well, we can do our F-test. Next to ANOVA. Thank you.